All right, so today we're going to be discussing higher level logic, all right, higher level logic. And normally when I talk of higher level logic, the first thing that comes to mind is predicates, all right? So we're going to discuss what predicates are. We discuss quantifiers. So we're going to talk of just two types for now, existential and a universal quantifier. And then we're going to see how we can use first order languages, which are predicate. And then we also look at the negations of quantifier statements. So that's basically what we're going to do. And each of these is very important because definitely these are stuff that you'll be tested on. All right. Now, what is predicate, or why do we need predicate in the first place? If you notice in section 1.1, we talked of propositional logic. So I will say a statement is a propositional statement provided that it is either true or false, but not both. All right. So it means there shouldn't be any form of confusion. Now, if I introduce a variable, for example, let's look at the statement here. X plus 3 is greater than 5. Obviously, this statement, you can't say if it's true or it's false because it can either be true or false. So it can even be both, you understand? The reason I'm saying so, because it depends on the value of X. For example, if X is 2, yes, it's fine. You can say 5 is greater than 5, which you can say false. It's fine. It's a propositional statement. But now, if you don't know exactly what X is, so it depends on what X is, this statement can either be true or false. All right. And because of that confusion, we need something called predicate. Now, what is predicate? So for this statement, we need to have a fix. All right. There should be a way that we can make this a propositional statement without any doubt, without any confusion. All right. So the first thing that they say is a statement is not a proposition. Very, very important. This is not a proposition because it can be true and it can be false. So the meaning you have that possibility means it is not a proposition. All right. And here they say it can be true or false depending on the value of X, which is true. We already know that. Okay. Now it will only be a proposition once the domain, you see the key here is that statement, the domain from which X comes from is specified. So if I specify the domain where X is coming from, then this statement becomes a proposition because it would either be true or it can be false, but not both. All right. Another statement, let's say we say there exists a number Y such that Y squared equals to 2. All right. Again, there is a problem there. You're saying that there exists a number Y such that Y squared equals to 2. Now the question is depend on what Y. So that the Y, where does Y belong to? You need to specify some sort of domain. All right. So without the domain, it is not a proposition. Let's go to the definition. They say given a domain, a predicate is a property that objects from the domain can have, right? Or a relationship between objects from the domain. For example, I can say that in the sentence above, I can say let P. I can say let P stands for is a student at UJ. So P on its own is called a predicate symbol. So if you notice it, I'm not associating P with any variable. So P on its own is just it's called a predicate symbol. Now, if I say that the sentence X is a student at UJ. So let's say that. So I move from is a student at UJ. Now I'm saying X is a student at UJ. Now in predicate, I can write it as P of X. You see, now I associate P with X, understand? We now call this a predicate, all right? So know what the difference is. You have a predicate. Predicate means you have a predicate symbol and some associated variable, all right? But a predicate symbol on its own is just that letter, the P. And please just use capital P to differentiate between higher level logic and lower level logic. So for predicate, we use capital letters. All right. For lower level logic, we use small letters. All right. Now, Since there's only one variable, which makes sense, there's only one variable, and the variable there's x. If you see, I say p of x. P of x means I'm only talking of one variable, x. We call this a unary predicate. So the word unary just means a predicate with one variable. But be careful. You can have a situation where you have more than one variable. In a case where we talk of binary predicate, we're talking of two variables. For example, I can say let Q stands for is a student at, then the sentence X is a student at Y, you can write it as the predicate Q X comma Y. All right, it's going to be the sentence X is a student at Y. All right, so you see you can have unary predicate, you can have binary. It can even go up to 3 variables or more. All right, but for now we'll try and stick to maximum of 2. All right, is there any question? Okay, I see someone is asking for the link to the WhatsApp group. All right, let's move on. Let's look at an example, example 1. Example 1, they say let Px be the predicate. X is a prime, all right? So X is a prime, and then they say with domain. You see, I told you guys, for this to be a proposition, you need to specify the domain, all right? So we say with domain Z plus, and some of you ask us, what is Z plus? Z plus stands for the set of all positive integers. Now I say write P1, P9, P13, and indicate whether each statement is true or false. So P1 obviously is going to, you're going to read it in this form. Is 1 a prime number? The answer is false. All right. I'll go back to the definition of prime number. We say prime number is a number that has just 2 factors. So, and the 2 factors is 1 and itself. All right. So 1 cannot be a prime number because it has 1 factor. It's just itself. All right. So 1 is definitely not a prime number. You need 2 factors. Let's look at 9. Is 9 a prime number? Again, the answer is false because 9 has 3 factors. It has 1, it has 3, and it has itself 9. So more than 2 factors is not a prime number. Let's look at 13. Is P of 13 a prime number? The answer is yes. It has only 2 factors, 1 and 13. All right. I hope that makes sense. And you see there, I'm just asking if the statement is true or false. So all you needed to do is to say false, true, and so on. Just tell me false, true, false, and so on. Just tell me. So in your test, if I say, is this true or false? All right. Just tell me if it's true or false. All right. If it's 1 mark, most of the time, if you say true or false, it's fine. You're going to get a full mark. But if I make it 2, obviously, I'm going to add a statement that you say motivate. You understand? Because some students are good at just saying true or false without even knowing why they say true or false. For example, someone will say this is false without knowing why. They just say, okay, 1 doesn't look like a prime number. All right, that's someone who doesn't even know a prime number. So you need to tell me 1 has only 1 factor, which is 1. But we want a number that has 2 factors, exactly 2. All right, 1 and itself. All right, if everyone is happy, let's move to example 2. Now, example 2, it gets a little bit excited. So I give you a binary predicate. Let Pxy be the predicate X is less than Y. Again, you see, I specify the domain. The domain is capital R, and that stands for the set of all real numbers. All right, all real numbers. And then I say write P minus 9 minus 10, P pi root 17, P 5 over 8, 6 over 10. Indicate whether each statement is true or false. Let's start with the first one. Minus 9 minus 10, you ask yourself the question, implies that is minus 9 actually less than minus 10? Remember, we're looking at this here, all right? We ask ourselves the question, is minus 9 less than minus 10? The answer is false. Actually, minus 9 is bigger than minus 10. So there is false. It's straightforward. Okay, for P into pi and root 17, is pi less than root of 17? The answer is yes, because you know pi is 3.14 root of 17, you get something like 4.123. So obviously 3 point something is less than 4 point something. So that one is true. Now, this is where I need to see understanding. I need to see that you understand. How do you tell me if this is true or false? The idea is that you're not supposed to use a calculator. So telling me straightforward that is true or false, I assume that you've used a calculator. So how do you prove to me that you didn't use a calculator? Bring everything to the same denominator. So this bottom piece here, bring them to the same number. And the easiest way to do that, just multiply top bottom by 5. Notice it? There you multiply top bottom by 5, you get 25 at the top, 40 at the bottom. And here, how do I get to 40? I just multiply top bottom here by 4, actually. You get 24 over 40. See, I bring them to a common base, or a common denominator of 40. Now I can compare them because now I know what I'm dealing with. So 25 over 40 definitely is bigger than 24 over 40. Therefore, this statement is false, right? So if I ask you this in a test, I expect to see this extra step here to prove to me that you didn't use a calculator. All right, I hope that was clear now. All right, let's discuss quantifiers. Guys, quantifiers are so important and you need to know this. It's a must. All right. In this section, we're going to focus on just 2 types. All right. So we're looking at the universal quantifier or the existential. So for the 2 types we're looking at, this first one here is like the upside down, like the A. All right. It says for all or for every. So when I say universal, it means I'm looking at the whole set. So everything. All right. And we call it universal quantifier. Now this E that is facing, we say the wrong direction, the opposite direction, is for some, or we say there exists at least one. All right, we call this existential quantifier. So for some, so we're looking at the subset of a bigger set. All right, so for some, or there exists at least one. All right, so we call that existential. And then we say that we can express 1 and 2 in formal language and informal language. Guys, this is where things get super exciting, right? What is formal language and what is informal language? When I talk of formal language, basically I'm talking of predicate. We're talking of first order language, all right? And the informal language is just your natural language. Another word for informal there is natural. It's like your English. Please, in this course, stick to English. When I say translate to informal, don't give me Zulu or any. Just write in English, all right? So formal language, first order or predicate. Informal, just give me natural language or say English. All right, just write in English. So now I give you this statement. All integers are real numbers. All integers are real numbers. Now I want to write it using predicate. All, once you see the word all, what's the first thing that comes to mind? This guy here, universal quantifier. So you say for all x element of z, remember z that stands for the set of all integers. So for x, for all x element of z, so I say for all integers, x is an element of R. What does that mean? It means all integers are real numbers, basically. So this first part here, we're talking about all integers. And if I say x is an element, I'm saying that R real numbers. All right. The z there, obviously, if you use z and r, we don't need to explicitly state that z denotes set of integers, because we all know that z denotes set of integers and r denotes set of real numbers. Now, there's something I need to mention, very, very important. Some of you're just good at using z to a point where when things change, you don't even realize that it has changed. Z says all integers. Now, if I do this, I say z plus. Now I'm restricted. I'm only looking at positive integers only. Positive integers only. All right. And obviously z minus. If I say z minus, we're looking at negative integers only. All right. So in the test, be very specific. If you don't put a plus or a minus, I'm reading it as all integers, positive or negative. All right. If you put a plus, it means you're telling me strictly positive. And you're going to see how useful these two are, right? Because the equations that will require you to choose wisely between one of these two. All right. Let's look at the next example. Now, the next example, they said there is a student who takes Math 01A1. All right. How do we write this using predicate? There is a student. You see, I didn't say all students take Math 01A1. I said there is a student. It means I'm talking of a particular student, right? So you cannot use universal quantifier. You need to use existential. Existential. All right. Existential, say there exists at least one. For some, it means when you're talking of a subset of a bigger set, you use existential. All right. So there exists an X element of S. You can see my predicate symbol here is capital X. Always use capital letters when you're talking of predicates, capital letters. So there exists an X element of capital S, and then I have a predicate called M of X. All right. But now you need to tell me, in this case, you need to tell me what S and M is. Don't just write this in a test and then you think I'm going to translate it directly that there is a student who takes math. You need to tell me. S there stands for the set of all students, the set of all students. MX is a predicate. All right. X takes Math 01A1. All right. I hope everyone is happy with that. All right. There are many ways of writing this. Someone can say, can choose a predicate here, S of X, and they have a different predicate on this side, and they try to combine them together. It works. But as long as you tell me explicitly what this S stands for, what M stands for, or any other letter that you choose to use. But like I said, they have to be uppercase when you're dealing with predicate. Any question? I see people are sharing links. All right. Join the WhatsApp group as soon as possible, because I will send more announcement in the WhatsApp group. So if you're not part of that, then you're going to miss out a lot. All right, let's keep going. Let's look at the truth value for quantify statement. All right. Let's start with that first one then. Let's look at the truth value. Now, they say for every X element of real number, so we say for all real numbers have squared equal to 1. So the square of any real number is equal to 1. Is that true? Obviously, that sounds so crazy, right? Because you can say the square of all any real number is equal to 1. And how do you show that that is false? You give something called a counter example. So in mathematics, if a statement is false, the only way to show that it's false is by giving a counter example. If a statement is true, however, you need to prove that it's true. All right, I'm going to explain that. In mathematics in general, a statement is true, you prove that it is true. All right. But if a statement is false, you give a counter example, just one example that makes it wrong, then the whole statement is false. All right. So in this case, because we know it's false, you can say the square of any real number is equal to 1. I just choose 7. You can choose 5 or 4 or 2, any number. You notice it doesn't work because 49 is not equal to 1. Right. Now, let's look at the second one. Now, this second one, you need to pay attention, right? We call this proof by exhaustion. When I use the word exhaustion, it means I have a set and I need to prove that this statement is true. I need to show that it works for every element in that set. All right. So they say for every X element of D, remember this D that's given as a set 1, 2, 3, 4, 5. They say X squared has to be greater than or equals to X. All right. Now to prove this, if it's true or false, like I said, if it's false, you just need to spot one that doesn't work. All right. That's your counter example, you're done. But if it's true, then you need to exhaust the whole set. You do proof by exhaustion. It means that you need to use each of these numbers here and show that it's true. Then the conclusion is that it's true. For example, 1 square is definitely greater than or equals to 1. 2 square is greater than or equals to 2 because 4 is greater than or equals to 2. 3 square is greater. You see, each of those are true. Because all of them are true, you conclude that it is true. All right. The restriction, you see, your domain has you restricted because of the domain. The domain here is just that set that contains numbers 1, 2, 3, 4, 5. All right. If everyone is happy with this example, let's move on. If you have a question, you can post in the chat area. Now let's discuss using first order languages. Predicate. All right. Now I'm going to emphasize on what's the difference between first order language and natural language. All right. It is important to be able to translate a statement from first order language. Remember, first order language is predicates, all right, where you see those quantifiers and predicates and so on, into natural language. Natural language is English, French, German, Portuguese, Zulu. Those are natural languages. But please, for my course, just use English. Oh, I'm so happy, all right? Use English, all right? It's very important to be able to translate to natural language, because not if I just write a predicate statement there and I don't translate it to natural language, someone might not actually understand what I'm trying to write. Hence, we'll teach you how to convert first order language to natural language, which in this case is English. All right, so we're just going to focus on English. Let's look at example 4. All right, please don't tell me that the English doesn't make sense because we're not teaching you English. My course is mathematics, not an English course. So just translate it as best as you can. All right, so let's start with A. You can see there is an existential quantifier there. So for some x element of real number, x equals to x cubed. All right, you can say they exist. Remember, this existential just means they exist, or there is at least one. All right, so I'll read it as there exists a real number. So this part here, there exists a real number, is just this first block here. There exists a real number, such that the number equal is cubed. You can see the number equal is cubed. All right. Someone can choose to say there exists at least one real number that equals its cube. Perfect. You get full marks. All right. So you can either say there exists for some real numbers, or you can say there is at least one. All right. And then for the second one, we have a universal quantifier. You know, it has to be for all. All right. We know already it is for all. So this first block obviously is going to say that all real numbers. And then the second block says the square cannot be equals to -1. So how do we do this? All real numbers are such that their squares are not equal to -1. All right. You can say all real numbers have squared different from -1. So as long as I hear that word, all real numbers, and they mention the fact that the squares is not equals to -1, you get all your full marks. All right. Let's look at the third one. They say all real numbers again. It shows that if they're negative, then their cube has to be negative. Okay, let's see. All real numbers are such that if the number is less than 0, definitely the cube is also less than 0. Well, you can write it that way, or you can just see that all real numbers that are negative. So all negative real numbers have negative cubes. I'm sure that should be the easiest way to write. So all negative real numbers have negative cubes. That's as easy as that. You want to go the long route, you go step by step. You start with the first block. You see that all real numbers are such that if the number is less than 0, okay, which is that one, then, because we see its implication, so it's if then, its cube is also less than 0. See, it's just you writing too much English, but you still get your full mark if you actually write it. But preferably, you can just say all negative real numbers have cubes that are negative. All right, easy. All right. Now we're doing things the other way. I give you a natural language, so English, and then I tell you to convert to first order predicate. Let's see. They said there is an integer greater than 2 and less than 3. There is. I use the word there is an integer. So I'm talking about one integer, right? There is an integer. So it has to be existential. Guys, once you get this first piece here wrong, the whole thing, I'll just make it wrong, right? So make sure you read carefully. When it's universal, I'm going to use the word all, every. When I say there is, it means I'm specifying, right? It's a subset. So it means that you need to use existential. So we say there is an x element of z. Remember, z is integer, right? Not, it can be positive or it can be negative, right? Set of all integers. So there is an integer, and then here they say that greater than 2, you can see x is greater than 2, and very important, and. So that's your and then they say less than 3, so you just say x is less than 3. All right. Or another student can do this because this looks like someone who really hated the topic of inequality. You can group this as 1, all right? So you can say there exists an x element of Z where x lies between 2 and 3, right? So this thing here is exactly the same as this one here, all right? So x simply lies between 2 and 3, right? They say no dogs have wings. No dogs have wings. Obviously, for you to be able to write this in predicate, you need to have a predicate symbol. In this case, we have a D there. D there stands for the set of all dogs. So dogs, all right, the set of dogs. And then WX stands for the predicate. You must remember this is D, capital D is predicate symbol. Capital W, because it's associated with an X, a variable, we call it a predicate, all right? And that predicate is X have wings, all right? F has wings. So I want no dog. So the important part is no dogs, all right? Guys, I'll tell you it's much difficult to write this in predicate than to say all dogs have wings. The reason I say is because when you say no dog, it means you're talking of all the dogs. So all dogs, they don't have wings, all right? So you have to start with universal. You need to start by saying that for all x element of D, means you're saying that all dogs, and then the second part, I have my predicate that says WX, where X stands for the statement X have wings. But I negate it. You see, the key here is the negation there. This negation says that all dogs don't have wings, all right? Where that W there stands for X have wings, all right? So you see, it actually works so nicely. And very important, when you do this, please just tell me what D stands for. Because you might assume to understand D and what W is. Just tell me D is a set of dogs. WX is the predicate X have wings. Done. You have your full marks. All right. Let's look at C. Every computer science student is an engineering student. All right. Let's see. So we say every computer science student. So first thing is, you need to tell me what student is, all right? So student, I have a predicate symbol there for S. So every X element of S means all students, the set of all students, all right? The reason why I'm using universal quantifier again, why? Because of this statement here. Every computer science student, every means all right, universal quantifier. And then say, if you're a computer science student, it means you definitely are an engineering student. So therefore, I can say my predicate CX, which means X is a student, or it's a X is a computer science student, implies that they are also an engineering student. But please tell me that S stands for the predicate symbol is a student, or the set of all students. Tell me that this predicate here is X is a computer science student. Tell me that this predicate EX stands for X is an engineering student, all right? So for all students are such that if they're doing computer science, then definitely they are also engineering students, all right? If you have a shorter way of writing this, good, but make sure that you tell me what your predicates are, all right? And they have to make sense. Don't just write symbols and think that I'm just going to understand. Example 6. All right, for example 6, they say, consider example 5C, though that example 5C that we did there. They say every computer science student, so we can write this in 2 ways. So you can call this one way of writing it. Obviously, everyone would love to write it the second way, right? This should be the easiest way. So yeah, instead of saying that I define what student is, I define what computer science students are, and I define what engineering students are, that's a lot of predicates. All right. The easiest way is to say I have a predicate symbol, C, which is the set of computer science students. Then I have a predicate, EX, that says X is an engineering student. So all computer science students, that's what that first bracket says. Then the second bracket just says they're engineering students. There we go. Every computer science student is an engineering student. Every computer science student is an engineering student. It's as easy as that. All right. All right. We only have 1 minute left on the clock. Let's discuss negation of quantified statements. Let's see if we can do some examples. All right. So negation of quantified statements. So the first two examples here, so this is just definition, right? And I'm going to go step by step just so that everyone is happy. Now, if I ask you to negate a quantified statement, these are the procedures. You need to negate each of these brackets separately, all right? So the negation of that whole quantified statement, if you negate for all, it becomes they exist, or for some, all right? So the only thing that changes there is this universal quantifier only. Only the universal quantifier changes. All right. And then in the second bracket, you also have to negate that predicate there. Let's look at the second one. If I say negate this, you negate the first bracket, meaning that this is going to change from existential to universal. You see my set of D there, this predicate symbol here is not affected. But now the predicate, you also have to negate it. All right.